So now that we have our fundamental theorem of calculus, right, our new method for evaluating definite integrals, let's see how we can use this, right? And what I want to do here is kind of take an approach you've seen me use before. I'm going to do these integrals two different ways. First, I'm going to do them using our geometry-based technique, thinking of these as areas, right? Then I'm going to turn around, use the fundamental theorem of calculus, and confirm that I do get the same results regardless of the method that I use. All right, so let's take a look at this first one. We've seen most of these before. This is, let's see, y equals x looks like this. And we're going from 0 out to 2. And that gives us this triangle. Right? It's a triangle whose base is 2 units and whose height is 2 units. So if we just think of this as area under the curve, then this is 1/2 of the base times the height. That's 2 times 2, which is 2. Over here, right, if we sketch this one out real quick, now we're going from here up and down, and we're going to go out to 2 again, and we get this shape here, and we've seen this one before. This is a trapezoid, right? This base is 5, and this base is 3, and the height is 2. So the area of a trapezoid is 1/2 the height times the sum of the bases. So that's 1/2 times 2 times 5 plus 3, which is 8. All right, and then finally this one here, let's see. This is the integral of 1 dx. I'm going to go up 1, not a dash line. There's my function. And I want to do this from -3 over to 5. So I'm looking at this rectangle here. So let's see. I mean, this is a rectangle, right? The length of the base is 8. The height is 1. So the area is 8. Okay, so here's what I'm going to do. I'm going to write these up here. Equals 2 equals 8 equals 8. All right, so let's hold on to those. Now we'll use our fundamental theorem, right, our new approach, and see if we come up with the same thing. Hopefully we will. Right, so I'm just going to clean up here. All right, let me get this stuff out from under here so I've got space to work. There we go, and I'll do it again over here. Okay, so my fundamental theorem says I need an I'm looking at the first one here. Says I need an antiderivative of x. Okay, I'm going to use x squared over 2. Now, here's one of the cool things about this fundamental theorem, right? You may be thinking at this point, very reasonably, what about the plus c? Because every time we talk about antiderivatives, there's always that plus c on the end. One of the cool things about the fundamental theorem, it says, and if you go back and look at it, right, you can check the exact wording on me. It says if cap f is any antiderivative, any one you want. Well, I'm going to pick the one where c is equal to 0 because that makes my life the easiest, right? And we'll circle back to this in a minute, right? I want you to see why it's okay that we can pick any antiderivative, but we'll come back to that on the next slide. Now, the way we write this, I need to evaluate this from 0 to 2. So I'm going to write this way. I'm going to put a line here, and I'm going to put 0 and 2. Right, so this is the notation we use. What this is telling me is it says put 2 in first, and we get 2 squared over 2, minus, remember that's what the fundamental theorem says to do. It's f of b, that's the top one, minus f of a, that's the bottom one. So this is going to be minus 0 squared over 2. And if I evaluate this, this is 4 squared over 2. That's 2 minus 0. Look at that. It worked. I got a match. Did exactly what the theorem said it should do. All right, now let's try it again. Now let's try it again. Let's try this second one, right? If I try to integrate this, I'm going to get, for an antiderivative, x squared plus 3x. I'm going to evaluate this from 0 to 2. If I put 2 in, I get 2 squared plus 3 times 2 minus, and here you're going to have to do this a lot. Group this second part. Right? I'm going to group it, and it's going to be 0 squared plus 3 times 0. This is, let's see, 2 squared is 4. 3 plus, whoa, sorry, it's not x squared. It's x squared over 2. In my head, I was having a little panic there because it was coming out wrong. So this is going to be over 2. 2 squared over 2, that's 4. Excuse me, that's 2. Plus 6 minus 0, which is 8. And it worked. I got to match again. As a matter of fact, I want to point something out to you real quick. Right? If we look at this my trapezoid over here, and we split it up into a rectangle and into a triangle and this rectangular base, right? This piece here is the area of the rectangle. And this piece, the triangle, I know the difference. This piece here is the area of the triangle. This piece here is the area of the rectangle at the bottom, right? And again, it comes out to 8, exactly like we expected. Okay, so how about this next one? What is the integral of 1? Well, the integral of 1 is just x from -3 to 5. If I put my numbers in here, if I put 5 in, this becomes 5 minus 3. 5 plus 3 is 8. And yes, once again, it worked. Right? So this is good, right? We're getting confirmation here. The theorem is, not only is it doing what it's supposed to, it's actually kind of helping, right? Being able to do this two ways kind of helped me out there in the middle, right? And it helped me to realize I was going off track a little bit. Okay, so let's try another one. Try this one. Okay, now we're out there, right? There's no way I could do this using geometric formulas because I don't have a formula for the area of this shape, right? E to the x, it looks like this. So the area that I'm looking for, if I go from 0 out to 2, is this piece here. I do not have a formula for anything even remotely resembling that curve up at the top of this thing. Okay, but that's okay because I got my fundamental theorem now. My fundamental theorem says, give me an antiderivative of e to the x. Easiest function to work with, right? Is it just like it's its own derivative, it's also its own antiderivative. So this is e to the x from 0 to 2. This should be e to the x. I'm going to put my numbers in. E squared, minus e to the 0. That's e squared minus 1. And that's it. See how useful this is, right? See how powerful this is, right? We'd have been here all day if we had tried to do this with Riemann sums and formulas for sums and limits and so forth, right? Here it took me all 3 lines. All right, so let me give you one to work with. Try this one. Right, see if you can work this one out real quick. Okay, an antiderivative of the sine of x. I'm thinking negative cosine of x. We're going to do this from 0 to pi. Right, so if I put pi in, this is minus cosine of pi. Now here, this fundamental theorem is great, but it involves these negative signs. And there's going to be lots of times where you have to be super careful to keep track of them all. This is going to be minus cosine of 0. Okay, cosine of pi, that's -1, so this is minus 1 minus cosine of 0, which is 1. See what I'm saying? More negative signs here than you can shake a stick at. So this is negative 1 is 1. Here negative 1 becomes plus 1. And now that's a weird result, right? You'd expect to, I don't know, you'd expect to have a square root or be some transcendental thing, but no, it's 2. Right, that's it. Area under, let's think about what this is, right? If I sketch real quick here, right, this is sine of x. This would be pi. So this is the area under kind of one arch, if you will, right, of the sine function. There you go. Okay, so what's next? Those are some nice examples, but if you go back and you look at these, I was very careful in the way I chose the functions that we were looking at, right? I chose them so that on the interval I was integrating over, the functions were always positive. If the function becomes negative somewhere on the interval that we're integrating over, we're going to have issues. Not bad, not unfixable issues, right? They're issues that we can work around, right? But we are going to have issues that you need to be aware of because it's going to involve an extra step or two. So that's what we're going to look at in the next lecture.